Um, okay, well, I'll check the recording later, but I think we're back recording. Right. What if you go to the other extreme? What if you make these extremely different? Like, what if one end is just an empty string and all the weight's on the other side? You have an empty string versus, would this be in pure free fall? So, guys, if it's in pure free fall, how fast would it be at the end of some interval? 9.8. How about square root 2GH? Hey, do you guys remember Galileo back here? The answer was root 2GH. Okay. Now, Sotwood's a little fancier looking, but if one of these masses was zero, this goes away, M2 over M2 cancel. Hey, look at that! It's square root 2GH. You see that? Yeah, that's pretty cool, isn't it? Okay. So speed at point B is square root 2, difference of masses, GH over sum of masses. Like that. Right, okay. All right, now let's put this to the test. I wanted to, yeah, because I think we'll have a couple spare minutes here. So I want to try this classic out with the old way, with dynamics and kinematics. And then, well, we just kind of solved it the new way, right? We got a general expression. So yeah, I guess we got to play the test against already. Okay. Let's throw some numbers in here. What if, so classic Atwood. Ooh, I got a number generator right here. Let's make one of these masses 52 units. The other one, whoop, not 52. 77. Okay. So what if this is 77 kilograms, something crazy, and this is 52 kilograms. Okay. And let's have a height change of 22 meters. So what if this moves down? H equals 22 meters, which means this is going to move up. H equals 22 meters, right? So we got like a huge outlet, right? Just a completely massive, right? It's going to look like several stories and something. Okay, so what would be the speed at the end of that motion? Now, the old way of doing it is you have to go through acceleration. Uh, so let's go through Newton's second law of motion. You guys remember net force over total mass? Guys, what is the force pulling down right here? mg equals what? 770 newtons. If I call g 10 meters per second squared. How much is this pulling down right here? 52 times 10, 520 newtons. That'll be true, right? For sure. Okay. All right. So I'm looking at 770 newtons, saying let's go clockwise. 520 newtons, 520 newtons, saying let's go counterclockwise. And that's acting on a total mass of 77 plus 52 worth of kilograms. Okay. So newtons over kilograms. Okay. When that would tell me how much it's accelerating just in general. Sure. So try that. So 770 minus 520, and then over 77 and 52. I'm looking at 1.938 meters per second squared. Okay, this is all using g equals 10 meters per second squared. Okay, so I'm using that. Okay. All right, so I got that acceleration. Guys, once I have that acceleration, okay, and if I combine that with this height change to figure out what is the speed at the end, which equation is that? Is that first, second, or third? Speed is a function of height change.
The first one?
I think it's got.
The
Yeah. It's got to be this one, right? Because the first two both involve time. I never mentioned how much time passed. Okay? You could solve for that, but here, if you jump straight to this one, I'll get it for you. Okay, here's your height change. Here's your speed. Okay. As long as it starts from rest. So I'm going to say v final squared equals v initial squared plus 2ax, just straight off this page. I'll start from rest. Let's just do that. Start from rest. Okay. So the final speed would be the square root of 2ax. So that's 2. Here's your a, 1.938 meter per second squared. And the height change was what, 22 meters? 22 meters. So let's see. What is the speed at the end of this? If it's square root 2, 1.938, 22. I'm looking at 9.23 meters per second. Right, is that okay? Do some numbers then? Right. Yeah. Now that's review. That's the old way. You guys could have done this like 3 weeks ago, right? Could have done it. Now let's try the new way, which we already have solved right here. Like we already solved it. we solved all the outputs right here. Okay, I can just plug in the values here, and I should get the same speed. See if I do. So what is the square root of CT? What are the masses? 7752. Okay, so 77 minus 52. G I'm calling 10. And the height change was 22. This is all over 77 plus 52. Okay, well, all those have units attached to them, but this is going to be meters per second, isn't it? Okay, equals V. So V equals, all right, well, what is all this? All right, moment of truth. We're going to see is physics all self-consistent. So square root, there's a bunch of stuff rooted. So I'm going to open up an excess of parentheses right here. Then 2, 77 minus 52, 10, 22 over 77 and 52. Okay, so I'm say, yeah, I think we're all right. Okay. All right. So you guys are following. Because when I hit enter, what number better show up on my screen? Yeah, it's got to be 9.23. Okay. Let's see. Oh, yeah. 9.23 meters per second. It totally works. Yeah, totally works. Here's the old way of doing it. Here's the new way of doing it. Same answer. That's good. All right. So last page on this packet. Ooh, we got some springs. I got a spring fires the ball vertically pew, to its maximum height. What do you think would be in the system? The what, and the what?
Gravity.
Yeah, the ball. Okay, if you're dealing with gravity, the object providing gravity is the
Earth.
Earth.
Oh,
Yeah, the ball, the Earth, and the
Spring.
spring. Yeah, because at some point there could be energy in the spring. Oh, now, okay, so I gave you guys really short blips here, so it's a little bit of imagination involved. But could you imagine that at point A, this ball is probably compressed against the spring? Okay. In which case, the energy would all be in the spring. And what's the expression for that?
Potential.
1/2
Yeah, 1/2 k squared. Yeah, that is spring potential. Yeah,
Oh.
yeah, 1/2 k squared. Okay, and then pew, fires up to the highest height. Guys, at the highest point, where'd all the energy go?
Middle ball.
Up.
Up.
Well, what? Here, I'm looking for.
Oh, it can.
Here's your options. Which one of these?
It can kinetic. Do it.
Is between A and B, does it have some motion, have some kinetic?
Yeah.
Yeah, but at point B, the highest point, is it moving at the highest point?
And no, it's
So
potential.
0.
It's all in GH. Yeah, it's all gravitational potential. Yeah. Guys, it's all in GH. That's where all the energy went. So yeah, I can give you numbers. You guys see there's 5 variables floating around. Now this term equals this term. So if I gave you any 4 of those numbers, you could calculate the 5th one. I have told you how stiff the spring was, how much compressed it, and knocked the ball and gravity. You could solve for how high does the ball go. Or if you know how high the ball goes, you could solve for one of these other things, like how stiff is the spring. Okay. Or how about this? What if I spring this Lego, goes up some height, and I go back and I smash the spring 3 times as far? Let's do a proportion. Guys, if you smash the spring 3 times as much, how much higher does it go? 9 times. It's that factor of 3 is getting squared. Yeah, that is. Okay. And what's the speed at the top? 0. And that probably wouldn't be the question I would ask you, but the answer is on this table. Let's go the other way. You drop the spring and smash the spring, or drop the ball, lands on the spring. You guys think it's still the ball, spring, Earth system? Okay. What kind of energy at point A?
Potential.
Yeah, gravitational potential, MGH. And then point B, what's a good guess? Maybe 1/2 k squared, something like that. Okay. And then, kind of depending on how you interpret it too. If this height drop also includes the spring compression, then actually actually it would be exactly this. Okay. If this height drop does not include the spring compression, this would actually be h plus x right here. Okay, so depending on exactly how it's given, it's really kind of a shorthand form for radius. Okay, do you guys think 0 speed at point B? Okay. All right, now these last 2 are a little bit challenge questions. All right, this one where the balls are you got some balls rolling without sliding. You see rolling without sliding? So I'm gonna say the balls in the system. How about the Earth? Because there's a height change. Ball, Earth. Okay. But I'm gonna throw one more item in the mix to make it a truly closed system, and that's the incline itself. Okay. And here's why. This ball would not be rolling unless there's static friction with the surface or some kind of friction, right? And I do want it to be static so that it's not slipping, right? And what that means is that that friction will induce rolling, but it won't actually take energy out of the system. So energy will still be conserved. Because normally if you see kinetic friction, it's like, wow, energy is going to dissipate away down an open system. Right? But this can still be closed. So what's going to happen is this ball is going to roll down the incline. Now, guys, if we have a rolling ball, does that sound like, ooh, yeah, all right, we're going to have to bring in this one, right? So be ready for that, and I'll show you guys kind of what's going on here. Right, so what type of energy at point A? Yeah, it's just empty H, that's all. Now, what if I didn't tell you H, but I told you L and let's say theta? Could theta be this angle right here? Somebody tell me, how do you get H based on L and theta?
Sine.
Yeah, L times sine theta. Yeah, you could. Right, if I told just like so many meters and this angle so many degrees, go L sine theta, that'd be the height. And then, okay, equals. By the time it gets to point B, well, okay, it's lost all its height, but do you think it's moving really fast and it's also rolling? So moving really fast could be which term? 1/2 mv squared. Translational kinetics, sometimes it's called 1/2 mv squared. Yeah. And then say also, so plus this rolling bit right here, 1/2 I omega squared. So also 1/2 I omega squared. Okay, guess that. Okay. Okay, so what is that? I bet you guys know what omega is. Guys, what is omega? Yeah, rotational velocity, angular velocity. Okay. You guys remember turntable physics, right? This omega is related to this v. You guys see here in gray, I gave a hint. It said omega is v over r. Okay, so these are related to each other, so you could do this little substitution. Now, what is this I? This I is called rotational inertia. I got actually a couple of rotational inertia sticks over there, right, where there's some weights, but they're just at different locations. Right? So we're going to talk about this maybe in December or January, somewhere in there. We'll talk about this type dynamics. Right? But it is like if you have objects that are rolling across the surface, they're going to roll differently. So that if you have them set on an incline, if somebody's going to win that race, right? They actually, finish it, go across the finish line differently. Okay. So it's kind of embedded in the eye. It's like, how is the mass distributed in the system? Right? So we're not actually going to solve this in class, so don't worry about this last box. Just we'll put a check there or something. But I just wanted to give you guys the setup so you can think about it. And then in the future, probably in a couple months, I start looking at that. Okay. And this last one, also sort of a challenge question. We got these asteroids in deep space. So they could be their own closed system. So I'm just going to say each asteroid. And there's basically nothing else nearby. Okay. And they started out some distance apart from each other and they just gravitationally track toward each other. Right. Now, as they do that, what energy form do you think you need to write for point A? Gravitational potential. Can you use MGH? Yeah, that one's not very good because that gravity field is always changing as they get closer to it's getting stronger. So you have to use this green one right here. Yeah. So it's negative GMM over R sub A. Okay. And here I said they were the same mass, so you could say M squared if you wanted to. GM squared over R. Okay. So, okay. I think what was it yesterday or the day before? Here, I take you guys through the story of derivation of escape speed, and through that, well, if you go back and look at that story, it's kind of an abstract idea, but in a universal context, potential energy is always considered negative, right? So don't forget to have a negative sign here. Okay, and then when they're closer to each other at point B, they have negative GMM over RB going on. Right? And then say plus, and wouldn't they be now in motion headed towards each other? So 1/2 mv squared for one of them, plus another 1/2 mv squared for the other one. Right? But they're the same mass. I bet they're pulling on each other the same. They probably have also the same v's. Just one's going right, one's going left. All right, you guys think? That makes sense? Yeah. All right, you guys get there? Good. All right. And then same with the Rolly one. We're not going to solve this in class, but I just want you guys to see the setup. Okay. If I threw some numbers at you guys, you could solve that. It's just some algebra, right? Okay. All right. So you backed up this? Okay, guys, double check, make sure your name's on the packet. You guys' names on your packet? Okay. If you have all 12 rows, then go ahead and turn that to the grade tray and I will give you guys some points in the grade book over the weekend. If you're missing some rows, then you can find the videos that are posted on Classroom and turn it in on Monday. But yeah, oh, we got perfect time left. So I'm just going to play a Vsauce video related to coincidences and science and math, and that will close out the week.
You're
Yeah.